A couple episodes back, we took a look at the proof of concept that we built, and while it looked amazing, it had a couple of issues. And the biggest issue was that the result register just didn't always work consistently. And I think this is due to the fact that the result register is transitioning on the rising edge as opposed to the falling edge. Because when we compare that to the actual MC14500 that we're trying to replicate, the result register in that actual chip changes on the falling edge. And I think that this is quite important given that the result register is getting its input from the logic unit, but also the output from the result register is feeding into the logic unit. So we can end up in this kind of weird loop. So what I want to do today is I want to take a look at a different D flip-flop design and see if that D flip-flop design will work better in our circuit. So we're going to use the proof of concept as a sort of test bed, which will be interesting given that it's mostly a complete thing. So we'll see if we can get that working well. But first, let's hop over to the bench and take a look at the type of D flip-flop that I'm thinking about building. So let's start with just a little bit of review of the D flip-flops that we've built up to this point. And this was actually the first D flip-flop that we built, and it's incredibly simple. It's just 4 NOR gates with a single inverter, and we were actually able to bodge the inverter by hooking our button up in such a way that it wasn't necessary. And we built this out of 4 6AU6s, but you could even compress this further and build it out of 2 60J8 dual triodes. So this is a really compact, nice D flip-flop, but it had a problem, and that was that if the data changed while the clock pulse was high, the output would change. So for example, if we put a 1 on the data and our output is a 0, when we toggle the clock and the clock pulse comes up, the output will change to 1. Now, while the clock pin is high, if the data changes from high to low, now we've got a double low into here, which makes the output of this high, and that high output feeds into this one, which pulls its output low, and then this high output gets fed up to here, which is the reset pin. And so while the clock is high, if the data goes low, it will reset the flip-flop back into 0. And so this can cause all sorts of problems from racing to timing issues. And so the actual usage case for these D flip-flops only is quite small. What we really need is a way to gate them. And that was when we came up with this design. And when I say came up with, I meant Googled gated D flip-flop and copied a design that we found on the internet. I didn't actually create this design from scratch. But it's also a relatively simple way of making a D flip-flop. I mean, you could do it with just 6 6AU6s. And actually, this is the D flip-flop that we used for our result register in the proof of concept that we built. And the inverter was handled on a different board. And you could simplify this even further down to 3 dual triodes. And I think the first time we built this, that was how we did it, so we could fit it on one breadboard really easily. But it's a really nice gated design. But as we saw on the result register for our proof of concept, it changes on the rising edge. And this, for probably reasons slightly out of my ability to grasp, is causing issues in our proof of concept. We have times where it's not switching, or maybe it's switching too fast. I'm not entirely sure what's going on. I tried to probe it with the oscilloscope, but I couldn't really see. There's just too many spots to check. And actually, I found that the oscilloscope probes were affecting the circuit just enough to cause it to behave even a little different. So this is a pretty interesting design. I mean, you can see that the right half of it here is still just an SR flip-flop like we have over here. All we're doing is changing how we control our input into this SR flip-flop. And to fully explain exactly what's going on in here and what signals are going where while we move the clock with our data as a high or a low is going to take a little bit of time to explain. But fortunately, I already did a video on this, so head back in time and watch the video on our gated D latch if you want to see more about this. But I think the reason that we're having trouble using this D flip-flop is the clock signal. So you can see we invert the clock signal here, but then only the inverted clock signal is being used, which means that pretty much everything has to happen whenever this clock signal goes up. There's no two separate steps going on here. There's just a really elegant single step happening. And I may not be explaining that correctly. There's probably somebody out there well more versed in D flip-flops than me that can explain it better. And if you are that person and you know, please let me know. I want to know if there's a better way to understand this D flip-flop. But the more that I thought about this, the more it felt like the solution needed to be a proper two-step type of flip-flop. And that's a design like this one down here. Now, this is often called a master-slave D flip-flop or a primary-secondary D flip-flop. There's a couple different naming conventions out there, but you can see that it's essentially two of these really simple D flip-flops ganged into each other. And I mean, you can see that's just a straight drop-in right there. So the way this works is that we have our data being fed into the first flip-flop here, and it's being controlled by the inverted clock signal here. So it really only changes state when the clock is low. And then we have the output of this first D flip-flop feeding into the input of our second D flip-flop. And it's controlled by the non-inverted clock signal. So it only changes when the clock is high. So essentially what we have are two of these flip-flops taking turns. You know, this one flips, and then when the clock changes again, this one flips. So what I think this is going to do is, by essentially having an entire D flip-flop sitting in between our data and our output, we can control that racing situation that I believe we're seeing. That situation where I believe that the result register flips multiple times and we're just getting an inconsistent result. So this is a really cool way to essentially break up setting a D flip-flop into two discrete steps. And I think that's going to make a massive difference in how the D flip-flop reacts with the input coming from the logic unit. So all that's left now is to build this on a breadboard and give it a couple tests. It's quite an intense build, so I'm not going to subject you guys to watching me place jumper wires for 3 hours. So we'll just go ahead and skip to the finished built version. All right, so that was an interesting thing to build up. You'll notice that there's quite a lot more going on this breadboard than you would be led to believe by just looking at the logic diagram here. But I ran into some problems while building it, both in as how much space that I have, as well as some clock issues, which we'll take a look at here in a second. But first, if you look back here, you'll notice that we have 4 6DJ8 dual triodes, and each pair of dual triodes makes up one of the D flip-flops down here. So this back pair is the first D flip-flop, and this front pair is the second D flip-flop. And because there's 2 triodes in each one, we can build essentially 2 NOR gates with just one tube. So that's quite nice. So what are these 3 6AU6 tubes doing up here? Well, this first one here is our inverter. So our clock is on this little black button here, and I needed to invert that to be fed into the 6DJ8s. But the problem with that is that the inverter feeds into 2 of the inputs. And so on all of the test ones that we built up to now, I never actually tested it with a 6AU6 inverter. So one of the issues that I was running into, particularly with building this D flip-flop, was that the output of the inverter was getting pulled too far down. And that's because of the way that I have my setup here. And that is that one input goes through a diode, then a 22,000 ohm resistor, then a 33,000 ohm resistor to negative 12 volts. And that negative 12 volts is pulling some of those electrons away from the grid. And it turned out that the inverter just wasn't strong enough to drive 2 inputs for these 6DJ8s. So I needed some way to make the output from my inverter stronger. And that is where the cathode follower helps out a lot. So you'll notice that the primary difference here is that there's no plate resistor, and the cathode now has quite a large resistor before going to ground. And really this resistor could just be eliminated and you could just have nothing to ground, but I like it there. It acts as a pull down in certain situations. But essentially the only thing that's slowing down the output here is just the internal resistance of the tube, and that's actually much, much lower than the 10,000 ohms of the plate resistor that we use on an inverter. And so we can get a much stronger push out of here. And because it's a cathode follower, it doesn't invert the output because the potential of the cathode just raises up to match the potential of the grid. And that's why it's called a cathode follower. The cathode follows the grid around. And so in this way, we can, whatever input we put onto the grid, we'll see the same on the output, but with a lot more push behind it. And so that's what I have set up here. Both of these 6AU6 tubes on the right are set up as cathode followers. This one here is the cathode follower for the inverter, and then this one here is a cathode follower for the button, because I kind of wanted to have an equal output being fed into here. I didn't want to have the button going straight into here. So that's what we have set up. We have an inverter, we have two cathode followers, and so this is kind of our clock unit, and then we have our D flip-flop on the back here. So right now I have the output of this final output here, which is going to be coming off of this 6DJ8 here. I've got that output running through a little LED, and I've got my data set up on this little toggle switch here, and the clock is this black button over here. So let's flip the power on and see what happens. Hopefully the LED will turn on and then dim out. Yeah, okay, so the LED turned on. Oh, there it goes. Yeah, so it dimmed out. All right, so our LED is off and our data is 0. And so if I push the clock, nothing should happen. Yeah, nothing's happening there. Okay. And if I toggle the data on and off, nothing should happen. Okay, yeah, that works. All right, so let's do a proper test here. Let's put our data at 1. And we'll toggle the clock. Now what I'm going to do when I toggle the clock is I'll push it down and hold it. And while I'm holding it, we shouldn't see the output change. But when I release it, that's when we should see the output change. So let's give it a shot here. All right, so push it. I'm holding it. Now I'm going to release. Yeah, look at that. The output changed. That's super cool. All right, so let's turn the data off here. Okay, that's good. That didn't change the state of it. So I can turn the data on or off, and the D flip-flop holds its state. So next I'll push the button. I'm holding it, and now when I release it, it should change states. Yes. Awesome, look at that. Okay, so that works. So it's changing on the falling edge. How cool is that? All right, so we've got it working on the breadboard now. The next step is to try to somehow hook this up to our proof of concept and see if we can replace this result register here with this breadboard. So let's give that a shot. Okay, it looks a little insane because we're missing a board here, but everything else is in place. And I've got all these jumper wires running across. So it looks like I'm playing the craziest game of Operation. And these two jumper wires were just a little too short, but I think they're making connection. We'll see. Hopefully it works. Also, I'm pulling power directly off of the power rail from the breadboard here. So white's 24 volts, black is ground, and blue is negative 12 volts. So the rest of this should be powered by my external power supply that's also powering my breadboard. And I'm doing this because I also need 6 volts because all of these tubes are wired up with their heaters directly to 6 volts instead of powering the heaters in series like I normally do. And so, hopefully it'll work. Let's flip the switch on and see what happens. So we should, if I flip one of these switches, we should have 24 volts on this. So if I flip one of these switches, we should see one of the VFDs illuminate here. Yeah, okay, there we go. All right, so that's 001, which is an XNOR. Let's do a load. So let's go 100. All right. And then we'll set our data to 1. Now this clock doesn't do anything because I'm using the clock that's on the breadboard. So this is actually my clock here. And I've removed the LED from the breadboard. So the only indication that we should see is here in the result register on our VFD here. So let's push the clock. We should see nothing. And then when I release the clock, we should see it store something. Yeah, look at that. Awesome. It stored a 1. All right, and so what that means is that whatever our logic unit was putting out, it's going through this yellow jumper here into the input for our D flip-flop. And this D flip-flop is now storing the 1 in it. And the clock controlled it separately. So, okay, let's do some toggle operations. So the one that we had the hardest time with was OR with the complement of the result register. So we'll turn data off and we'll turn this to 101 because that's OR with the complement of the result register. So when I push the button, the result register should stay the same, but when I release it, the result register should go off. Yes, it went off. Now let's see if it comes back on again. Yes, it comes back on whenever the button is released. It's changing state on the falling edge. That's super cool. All right, let's try the XNOR operation, and that's 001. All right, so again, it should toggle back and forth. Yeah, there it goes. There it goes. Yeah, that's toggling pretty consistently. Yeah, that's super cool. That's awesome. All right, so it looks like this thing is working amazingly well now. Unfortunately, the breadboard itself is as big as the entire proof of concept. So I don't think I'm going to cut a new board for the proof of concept. I quite like the original board that we had here. And the proof of concept was a proof of concept. And I think it's an awesome, beautiful conversation starter. But what it means is that now we have a design that works for our final version. So now we just need to focus on figuring out how to design this using 6 AU6s in a package that's somewhat compact. But man, I could not be happier with how that turned out. That is epic. That is so cool. Oh man. All right, well, I'm going to keep playing with this and trying to experience all of the flaws and wonderfulness of my essentially ER looking breadboard proof of concept combination here. But thank you guys so much for watching, and we'll see y'all in the next episode.